What is a car? We have two images here. Which one is the car? Is this the car? Or is this the car? If we wanted to have a model of what a car is like, you could argue that this one is the car. This is the right size in terms of the dimensions of the chairs where the passengers will sit. This is not a car, because people can't fit in that. It's too small. But this is not a car. It doesn't have wheels. These are representations of cars, but neither of them are real cars. These are models to describe, in this case, how it looks, and in this case, the scale of the chairs in a car, but neither of them are cars. What is the next picture? This is not a pipe. It looks like a pipe, but it's an image of the pipe. This is an important painting by Magritte, who really hit the nail on the head by saying that this art that we have is only a representation of reality. It's not reality. It's not the way it is. This is a model. This is a way of representing something. And this is what we have in physics. In the world of physics, we use models to represent the way things behave or the way things look. But it's still a model. It's not actually what it is. Let's get back onto the wave-particle duality. Is light a wave or a particle? Sometimes its behavior can be explained as being a wave, interference, refraction, diffraction. Sometimes it behaves like a particle, the photoelectric effect. So which is it? Is it a wave or is it a particle? And this brings us into the quantum world, wave-particle duality. Richard Feynman said, "Things on a small scale behave like nothing you have any direct experience about. They do not behave like waves, they do not behave like particles, they do not behave like clouds or billiard balls or weights on springs or anything that you have ever seen." Now let's look at the quantum world. If light behaves like a particle, is it possible that a particle can behave like a wave? And this is where we cue de Broglie. Describe the de Broglie hypothesis and the concept of matter waves. So he thought matter can behave like waves. IB say in the syllabus that students should be aware of the wave-particle duality of both radiation and matter. We know from the photoelectric effect that waves, or light waves, can behave like particles, and we call this the wave-particle duality of light. And maybe particles can behave like waves, which is a wave-particle duality of matter. And this is where de Broglie came in. He suggested that matter can behave like waves, and a convenient unit of a very small particle would be electron, and he said that when it's accelerated it will start behaving like a wave, and the wavelength is given by h over p. P is the momentum, h is the Planck's constant, and lambda is the wavelength. This is a definition that is often asked. So we need to outline an experiment which verifies the de Broglie hypothesis. We have a filament where electrons are accelerated and they're fired at a nickel crystal. And then we have a detector. These electrons kind of bounce off. Okay, particles can do that. Particles can bounce off things. And then basically, so at a scattering angle, the particles just bounced off, and when you had the detector at different angles, you were able to detect where most of the particles were going. Fine, this is these are electrons behaving like particles. Read that. But when we fire rays at a crystal, for example, we get an interference pattern. By firing the wave here, some waves go to the next level of atoms, and they wouldn't interfere with those that were reflected from the top, so we get an interference pattern. So When you accelerate an electron, it will start behaving like a wave. It will demonstrate diffraction and interference. So when you fire electrons, one explanation of why there's a particular reading here is because of the interference pattern here. And basically by changing the accelerating voltage, in other words changing the speed or the momentum of the electrons, found that the angle at which you got the readings of the electrons changed. That means that basically the wavelength of the wave is changing. So peaks at certain velocities or momenta correspond to certain wavelengths, and these actually agreed with the Broglie wavelength, which was lambda is equal to h over p. So they knew from X-ray diffraction, and they were able to accelerate electrons with the same wavelength, and it completely agreed. So there was agreement between the de Broglie wavelength and the interference pattern given by crystal scattering. Now, here is an excellent description of the quantum world of electrons. How sometimes electrons behave like particles, and sometimes they behave like waves.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
We have to solve some problems involving matter waves. For example, students should be able to calculate the wavelength of electrons after acceleration through a given potential difference. The IB say that you specifically should be able to do this calculation, so I've gone through an example here. You can try this now. You know, the voltage is 1000 volts. Planck's constant is this. The mass of an electron is this. So we use this equation. H is equal to m over v, but you need to find v. How do you find v? Well, you find the kinetic energy. The kinetic energy is being given by EV. So you have to get this answer. So I'll help you a little bit. The kinetic energy is EV, which is 1.6 times 10 to minus 19 times by 1000. Gives us a kinetic energy of 1.6 times 10 to the negative 16 joules. This is equal to half mv squared, and from that we can find v. You can try that. So you should find this value for v. Sometimes it might be easier, instead of using half mv squared, is to use p squared over 2m. So we use the Broglie equation is equal to h over p. You know what v is, you know what the mass is, you know what h is, so you find out that the wavelength will be equal to 4 times 10 to the negative 11 meters. Another example. This time we have to do it, the equation the other way round. Light has a wavelength of 5.04 times 10 to the negative 7 meters. What voltage is needed to accelerate the electrons to the same wavelength as this? You know what the wavelength is, so you find out what the momentum is. From the momentum you find out the kinetic energy. From the kinetic energy you can find out the voltage. So you can try that now. And the answer is here. So, the wave-particle duality, a summary. Let's look at the first one. Wave behaves like a particle, the photoelectric effect, or the Millikan's experiment. The particle wave, to show that particles behave like waves, is a Davison-Germer experiment. Some details. We know that photons cause emission of photoelectrons. And here we know that electrons diffracted and interfere after collision with crystals, nickel crystals in particular. Some more details. There's a delay, the color or the frequency, and brightness are the three factors which are peculiar to this experiment. One is the delay. There is no delay. Immediate emission of photoelectrons. Secondly, red light gives no emission. The third point, the brightness only changes the current, the photocurrent, and not the maximum energy. The maximum energy depended on the frequency, in other words, the photon energy. The further details of the Davison-Germer experiment, the interference or diffraction pattern agreed with de Broglie's hypothesis. Lambda is equal to h over p. Equations, the photoelectric equation, and lambda is equal to h over p. An explanation: photons come in packets called photons, and electrons can behave like waves.